Hello everyone. Good evening guys. So tell me whether audio and video is clear or not. Please check whether audio and video is clear or not. I think audio and video is clear from my side. Please check your side. Okay. So good evening guys. Good evening everyone. Good evening. Good evening. Please tell me whether audio and video is clear or not. Tell me whether audio and video is clear or not. Everyone, please tell me. Because from my side it's clear. From my side audio and video is clear. Okay, yes, it's fine. Okay guys, so let's start the session. So in this session we will discuss about logarithmic plots, because in control systems, especially in Bode plots, we deal with these logarithmic scale. Okay, so in this fundamental series, control system fundamentals, I am going to teach you about logarithmic plots in today's session, and this session is important as far as Bode plots are concerned. So you can see, I can say that after this session you will be able to understand Bode plot partially. Okay, not fully but partially you will be able to understand Bode plots. Okay, so let's start the session, and first let's cover the introduction part, and then we will go to the plots. Okay, so this is my introduction. My name is Asu Jangna, and you can start your preparation with me. I teach almost every subject in electrical engineering, so you can continue your preparation with me on BYJU'S exam prep. Okay, so there is a free workshop if you want to prepare for GATE 2024. So there is free workshop at 7:30 p.m. today itself. Okay, so you can join this workshop. This workshop will be taken by Dheeraj Sardana sir, and it will be at 7:30 p.m. and today is 9th May. So on the same day you'll get this free workshop. Okay, so you have to register first. Link is given in the description, so you can join this workshop. This is about results from BYJU'S exam prep GATE 2023. So you can see that under 50 there are 62 students, and under 10 there are 13 students. So I mean, the results are very excellent, so you can join our platform. So guys, first you have to give the Guru Dakshina, and the Guru Dakshina is you have to subscribe our channel. If you haven't subscribed it, please subscribe it and press the bell icon so that you get the notification whenever my sessions are live. And don't forget to like this session. Okay, so please like it. Okay, let's start our discussion. First of all, to understand the logarithmic plots, what I need to do is, first I will tell you about some logarithmic log characteristics. Okay, so let's first discuss about log scale, log or maybe properties of log. Okay, so first we have to understand that, and then we will try to understand the distance between 2 points in terms of decibel or in terms of decade or octave. Okay, so that we will try to understand how to calculate the distance between the 2 points in terms of decade and octave, and then we will try to look at the slope and the plot, how to do the plot and what is the meaning of slope, that we will try to understand. Okay, so let's start this session. So first of all, logarithmic properties. So the first property I want to say is, let's say, okay, wait a minute. Okay, let's say something is given like this: log base a and x equal to b. Let's say it is written like this. Okay, let's say some equation is given like this. Now what you can do is you can always calculate x from there. So you can say that from here I can calculate value of x. X will be equal to a to the power b. It means the base will remain same. Okay, you can also call it anti-log. Okay, so what I have done is I have taken the log of x and base a, that is equal to b, let's say. So from here you can calculate the value of x. So the value of x will be, the base will remain as a to the power b. Okay, I hope you got the point. So you have to remember this, it's very important property. According to this property, you can say that if I say that log a and x is also a, then this value has to be 1. If the base value and this x value, if they are same, then this value will become equal to 1. You can see that. You can see what value of b should I take so that x become a, because I have taken x as a. So what should I choose this b so that x become a? So b has to be 1. Okay, then only x will be a. So you can, in this relation, you can put x as a, then b has to be 1. Okay, So I hope it is clear. So when the base and this x is same, you'll get value as 1. Okay, so you have to remember this property. Now let's come to the next point. Let's say I have log a xy. So what you can do is you can break this x and y like this. Log a x plus log a y. Okay, so you can break it like this. When x and y are multiplied, then and they are given in logarithm. Okay, so what you can do is you can break it like this. Similarly, if you say log of a base a and x upon y, so what you can do is you can write it like this. Log a x minus log a y. Okay, you can write it like this. I hope it is clear. So you can write it like this. Again, this is true. Okay, now property number 4. So in property number 4, what you can do is you can say that log a x to the power n, that will become, I mean, this power you can take it out. So it will be n log ax. Okay, n log ax. So you can write it like this. I mean, this power will come out. So you have to remember these properties. There are some other few properties are also there. I mean, if you have understood this property, so if I say log a and if I take 1 here, then it will always be 0. Okay, it will always be 0, and you can prove it. From where you can prove? Using this relation you can prove this. If I take x as 1, what should be the value of b? Now x, if you put x as 1, then log a1 equal to b. Log a1 equal to b. Now if you take anti-log, so you can say that x is 1. 1 is equal to a to the power b. Now what should I take this b so that it become equal to 1? So obviously b has to be 0. Okay, using this property you can prove this relation. So whenever in log you get 1, it will always be 0. And remember this property. This is again very important. Whenever you have multiple power like this, so you can take this power out. Okay, and you can write it like this. I hope it is clear. Now let's move further. And so I told you about some properties of log. If you know these properties, then it will be easy for us to understand logarithmic plots. Okay, so let's calculate the distance between 2 points. Let's say there is an axis. You can call this axis as omega axis. Okay, omega, radian axis, a radian per second. It's frequency axis. On this frequency, let's say there are 2 points. Let's say this is 5 and this is 20. Okay, this is 5 radian per second, this is 20 radian per second, and I want to calculate the distance between these 2 points. Now this distance generally we calculate in terms of decade or in terms of octave. Okay, how much octave is this distance, or how much decade is this distance? So we measure this 2-point distance generally in decade or octave. Now how to calculate this distance in decade? Okay, so whenever you calculate the distance in decade, what you can do is log base 10. You take the base 10, and if you want to calculate this distance, so the higher value divide by the lower value. So this much of decade is this distance. Okay, this way you can calculate the distance between 2 points, this much of decade. So it will be, you can say that it will be log 10 and this 4. Okay, because it will cancel and it will become 4. So this much of decade is this distance. So this distance is this much of decade. Now generally decade means 10 times. If there are 2 points and 1 point is 10 times of the other, then we call that we have moved 1 decade. Let's take an example. Let's say this point is 10 and this point is 100. Okay, now if you want to calculate the distance between them in decade, so what you can do is, while calculating the distance in decades, what you need to do is you have to take this point in the numerator, I mean the highest value point in the numerator, and this lower value in the denominator, and you can calculate this. So it will become log base 10, and this will again be 10. Now the base value and the x value are same, so it will always be 1. It means if you are moving 10 times, so you are traveling 1 decade. Okay, you are traveling 1 decade. I hope it is clear. So whenever you move 10 times, you are moving 1 decade distance. So you have to remember this. Similarly, there is one more way to represent this distance, that is octave. Okay, octave. How to calculate this distance in octave? How to calculate the same distance in octave? Generally, oct means 8, but octave means double. Here the octave meaning is double. So if you want to calculate the distance in octave, then what you need to do is you take log 2, log base 2, and this distance upon this distance. So 20 upon 5. Okay, so it will be log base 2, and here you have 4. Okay, here you have 4. Now in 4 you can see that 4 can be represented as log base 2 raised to the power 2. And now this 2 will come out, so it will become 2 log base 2, and x is also 2. So this will become 1. So it will become 2 octave. 2 octave. Octave means double. If you are moving 5 to 10, let's say you are moving 5 to 10, it means you are moving double distance. It means you are traveling 1 octave. Now again, 10 to 20, it's again double. So this is also 1 octave. So the total distance is 2 octave. I hope it is clear. So whenever you are measuring the distance in octave, you have to look at the double distance. 5 to 10, it's doubling. So it's 1 octave. Next, 10 to 20, again it's 1 octave. So this is 1 octave, this is also 1 octave, because you are doubling the distance, doubling the point. 5 into 2 is 10, 10 into 2 is 20. So this is 1 octave, this is 1 octave. So the total distance is 2 octave. And whenever you want to calculate the distance between 2 points in octave, what is the method? The method is very simple. You have to take base 2. Okay, base 2 and this final distance upon initial distance. Okay, final point upon initial point. So this will be my octave. Whenever you want to calculate the distance in decade, then what you need to do is you have to take base 10, final point upon initial point. Octave means 10 times and decade means 2 times. Let's say you move between 2 points. Let's say this is 1 point. Let's say you are moving from 1 to 10. So it means you are multiplying by 10. If you are multiplying by 10, it means you have moved 1 decade. 1 decade. This distance is 1 decade. You can also calculate using formula that I just told you. So what you can do is whenever you calculate the distance between 2 points in decade, what you need to do is you take base 10. This point upon this point. So you can take 10 upon 1. So this will be my decade. This will be 1 decade. So whenever you are moving 10 times, it means you are moving a distance of 1 decade. Okay, 1 decade. Now how much octave is this? How much octave is this? So you can calculate this value in octave also. The only thing is you have to take base 2 and it will become 10 upon 1. It will become 10 upon 1. Okay, this will be 10 upon 1. So now you can calculate this value. If you calculate this value, can you calculate this value? Log base 2 10. What is this value? Tell me guys. What is this value? Log base 2 and this value is 10. So you can calculate this value and this will be my octave. This much of octave. So if you can calculate this value, let me check how much value I get if I use the calculator to calculate this. So log, wait a minute, I have to set the value of log. So I think it's not working, my calculator, because I have to set the base now, because my base is already, I mean, by default it is taking base 10, but I have to change the base as 2. So you have to calculate this value. Tell me guys, what is this value? If you can calculate this value, what is this value? Base 2 and 10. If you can calculate this value, it will be very helpful for me. Okay, so this much of octave, this much of octave. Okay, so the same distance, which is 1 decade, you can also calculate the same distance in octave. Now you get a relation. And what is the relation? Log base 2 10 octave is equal to 1 decade. Okay, so this is my one relation I got. Now you can calculate this value. If you can calculate, if you can tell me in the comment section, what is this value? Log base 2 and 10. What is this value? Okay, so that much of octave equal to 1 decade. So you have to remember this relation. Okay, but I actually don't remember because I don't require that, but you have to remember it. Okay, so whatever this value came, I think it will be 3 point something. Okay, it will be 3 point something. Okay, 3 octave, 3 point something 3 octave equal to 1 decade. Okay, so you have to remember this. Now let's come to the next point. Okay, let's come to the next point. So I told you how to check the distances and what is the relation between decade and octave. So 1 decade means this much of octave. You can calculate this value. In the comment section, if you can tell me, that will be a great help. Okay, but I don't think that you are understanding this point, because otherwise you must have commented. Okay, if you got this point, tell me guys, what is this value? Log base 2 and 10. If you can calculate using calculator. Okay, let me check, because you are not doing it. It will be, yes, it will be 0.30. Oh, wait a minute. I think it will be log base 2. No, it's not correct. Please check it. Okay guys, so you do it yourself. I think it will be 3 point something. Okay, 3 point something. You can do it yourself, because I don't have calculator. So in my mobile, the calculator is not working. That's why. Anyway, so you can calculate the distance between 2 points. You can calculate the distance in decade as well as in octave. If you are moving 10 times, it means you are moving 1 decade. And if you are moving if you are doubling the distance, it means you are moving octave. So I told you how to check the distance between 2 points in octave as well as in decade. Okay, now let's come to plots. Let's come to logarithmic plots. First of all, why you need logarithmic plots? Why you need logarithmic plots? Let's say I want to plot a function. I want to plot a function f omega with omega. Okay, let's say I want to plot a function f omega with omega. Obviously, you have to plot this function for a higher value of omega. Let's say at 10 to the power 5 radian per second, you have to check what is the value of this function. At omega equal to 10 to the power 6 radian per second, you have to check what is the value of this function omega. You have to plot that. So at very high frequencies, you have to plot, you have to draw the wave shape of this function f omega. Now it's difficult. If you want to plot this graph on a linear scale, then it will be very difficult to plot. Why? If you look at the linear scale, like let's say this is my linear scale. So on linear scale, the problem is, let's say this is 0 and you call it 1 radian, you call it 2 radian, you call it 3 radian, you call it 4 radian, and you call it 5 radian. Okay, so let's say this is a linear scale and this is 1 radian per second. This is 1 radian per second. This is 1 radian. So if you are going on a linear scale, you will not be able to reach at this point. Why? Because it's very large. You have to take many steps. It means on linear scale, this large value cannot be representable. You can't represent this value. Now many students will say, sir, why don't you take this as 0, this as 100, so this will become 200, this will become 300, this will become 400, this will become 500. Again, to reach this point, you have to take many steps. So it will be very large graph, okay? Very long distance you have to travel. So why don't you take 0, 1000, then next point is 2000, next point is 3000 and 4000. Why don't you do it like this? Again, to reach this point, you have to take many steps. It means if you are taking this as 0, then you have to take this as 10 to the power 4, then this has 2 into 10 to the power 4, then this has 3 into 10 to the power 4, and then 4 into 10 to the power 4, and then after 10 steps you have to reach, you'll reach here. Okay, after 10 steps you will reach here. But then it is difficult to show this point, because then you have to take 100 steps to reach here. So again, these high frequencies are very difficult to show. Okay, it's very difficult to show on a linear scale. The problem is this, I mean, you are moving in a fixed distance. Okay, that's why it's very difficult to show these actual these large of actual frequencies. Okay, you have to take many steps. Okay, let's say this step is of 10 raised to power 4 length. This is also 10 raised to power 4. This is also 10 raised to power. So if this is 0, this will be 10 raised to power 4. This will be 10 raised to 2 into 10 raised to power 4. This is 3 into 10 raised to power 4. 4 into 10 raised to power 4. It means every step is of 10 raised to power 4. Now to reach 10 raised to power 5, you have to take 10 steps. And to reach 10 raised to power 6, you have to take 100 steps, which is very long distance. I mean, you have to travel very long. It's very difficult to show these points. You have to take very large graph. That's why we want to approach log scale. We need to show omega on log scale. Now, what is the advantage of showing log scale? What is the advantage of showing the points on log scale? The advantage of showing these higher frequency on log scale is you can show all these frequencies easily. Now, let me show you why. Let me show you how you can plot these frequencies easily. Okay, let's say I have this omega axis and I want to show the points on log scale. It means, let's say this is 1. This is actual frequency 1. And this is 10. This is 100. This is 10 raised to power 3. This is 10 raised to power 4. Now what I'm doing is, I'm representing the actual values. These are the actual frequencies. But if you look at these points carefully, I am showing equal distance between 1 and 10 and 10 and 100 and 100 and 1000 and 1000 and 10,000. I am showing equal distances because on log scale, these distances will be equal. Why these distances will be equal? If you calculate this distance in decade, let's say, since you are moving 10 times, every step is of 10 times, you can see that. And in 10 times, I know that the distance is 1 decade. So it means this distance is 1 decade, this distance is also 1 decade, this distance is also 1 decade, this distance is also 1 decade. It means on log scale, on log paper, you are moving equal distances. But actual value is 10 times. You know that you are moving 1 decade. From this point to this point, again 1 decade. It means on log paper, this distance and this distance has to be equal. But actually, you can see that you are in one decade, you are moving 10 times, 1 to 10, and then 10 to 100, and then 100 to 10 is to power 3. It means actual values, every time you are doing 10 times. But in decade, this distance is 1 decade, this is also 1, 1, 1. So on log scale, you are at equal distance. On log paper, you are at equal distance, but actually, you are moving, every step is 10 times ahead. Okay, I hope it is clear. Tell me, guys, tell me everyone, have you understood it or not? Okay, have you understood it or not? I hope it is clear. So I told you what is the meaning of log scale. What is the meaning of log scale? Why you require that log scale? Because the actual value, if you are using linear scale, it's difficult to show these higher values, 10 raised to power 5. If you have, let's say, for somehow you showed 10 raised to power 5, you showed 10 raised to power 5, then it is difficult to show 10 raised to power 6. You have to take 100 steps. You need very large distances, okay? Very large log paper. But if you are using log scale, then on log scale it is easy to show. You can see that. On log scale, you are showing actual values. But these actual values are not on linear scale, they are on the log scale. And on log scale, every 10 step, every 10 times, the distance between 2 points is equal. You can see that from 1 to 10, it's 10 times. You are moving actually 10 times. It means 1 decade you are moving. From 10 to 100, again 10 times, it means 1 decade. This is also 1 decade, this is also 1 decade. So, and 1 decade, every step is 1 decade. So the distance between these 2 points will remain same on log scale. I hope it is clear. So this is the advantage of showing the points on log scale. Okay. But there is a disadvantage of this log scale also. What is the disadvantage? Let's say you want to go back. Let's say you have shown 1 here. Now, if you move 10 times distance in this direction, let's say, so this has to be 0.1. This has to be 0.01 because you are moving 10 times down. I mean, you are decreasing the values. You are moving, every step is of 1 decade. So on this side, it is multiplying, every step is 10 times of the previous value. Now you are moving back side. So every step is 10 times less. Okay. So if this is 1, this will be 0.1, this will be 0.01, this will be 0.001, this will be 0.0001. So you cannot reach at 0 point. You cannot reach as exactly 0 point. You have to take infinite steps. You have to take infinite steps to reach exactly 0 point. This is the disadvantage of showing on the log scale. So whenever you show any graph, and if you take this axis on log scale, let's say, if you take this axis on log scale, then at this point you can't say 0. Because if you say that this point is 0 radian per second, then you will not be able to show 1 radian per second, because to reach at 1 radian per second, from 0 to 1, you have to take infinite steps. Okay, this is the disadvantage. So at this point, don't show 0. Whenever you are showing this log scale, don't show this as 0. You can show this point as 0.1. You can say that this point is at 0.1. Okay, this point is at 0.1. This is not origin. So if this point is 0.1, this point will be 1, this point will be 10, this point will be 10 is to power 2, this point will be 10 is to power 3, this point will be 10 is to power 4. I hope it is clear. So every 10 times you move, it means you are moving 1 decade. Okay, I hope it is clear. Okay, so I told you that you have to be careful on log scale. Don't show this point as 0, because once you have showed this as 0, you will not be able to reach to 1. And you can see it from here. Let's say I have shown 1 here. So if I'm showing 1 here, then 10 times you move, this will be 1 decade distance. Further 1 decade, this will be 10 is to power 2, this will be 10 is to power 3. Similarly, if you move back, if you have showed 1 here, then you will not be able to show 0, because for 0, you have to move infinite steps. Okay, this will be 0.1, this will be 0.01, this will be 0.001, this will be 0.001. And further you have to drop, every step is 10 times less. Okay, so you have to apply infinite steps to reach at exact 0 point. It means if you have shown 1 here, then 0 will not be, you will not be able to show 0. Similarly, if you have shown 0 at some point, let's say 0 is shown on the log scale, then it will be impossible to show 1 on this scale. You can't reach 1 because you have to take infinite step on this side. That's why we don't start with 0 on log scale. Generally, we start with 0.1 or 0.01 or 1. Okay, so you can start from this point. I hope it is clear to everyone. I hope it is clear. So this axis I have shown in the log scale. Now look at the amplitude axis. Generally, this amplitude axis, wait a minute, let me show. Okay, let's take a graph. So let's take, this is as radian per second axis, omega axis, and this is under log scale. I have given you the reason why I'm showing it in log scale. And let's say this is my f omega function. This is my magnitude. But I don't want to show the magnitude axis. I don't want to take this axis in terms of actual magnitude. Why? Again, what I'm doing is I'm taking this magnitude in decibel, dB. In dB. I am representing this magnitude in dB. How to take in decibel? How to convert this magnitude in decibel? So whenever you want to convert this magnitude in decibel, then what you need to do is, let's say this is some voltage function or whatever function, okay, voltage or current or whatever, okay. Then to convert this in decibel, what I need to do is I need to take 20 log base 10 of FW, okay. So it will be my decibel value. So you can convert every value in decibel like this, 20 log base 10, okay, 20 times of base. This will become this much of dB, decibel, because generally I'm taking this as voltage or maybe current. But whenever this FW is power, whenever this represent power, then you have to take 10 log base 10. You don't need to take 20. You have to take 10 log base 10. So you have to remember this point, okay? So I told you how to convert any value in decibel. So this amplitude has to be in decibel. This amplitude has to be in decibel, okay? So you have to take this amplitude in decibel. The good point is, in decibel, you can represent these points. I mean, the large decibel, a large actual value can be converted into small decibel value. So it's kind of changing the currency. Like if you are taking very huge amount of money, then you generally talk in terms of dollar, not in rupees, okay? So you talk in terms of dollar. Why? Because dollar is a big currency, no? Because approximately 80 rupees is equal to $1. So that's why you deal in dollars, and dollar is, you can say, universal currency. So that's why I mean, not universal, because many countries deal in dollar. So that's why you always convert in dollar. So it's the same thing. What you need to do is you convert the magnitude in decibel. Okay. So this is the, this amplitude is in decibel and this will be in log scale. So now we need to plot a graph. Let's say some graph is given. Let's say there is some graph. Let's say this graph is given. Some function is given in decibel and this is some graph. Now look at this line. Let's say this point is at 1, okay, and this height is 20 dB. And the slope is minus 20 dB per decade. This is the slope of this line. Minus 20 dB per decade. Now, what is the slope of this line? Since height is not changing, so you can say that slope of this line is 0 dB per decade. There is no change in slope. There is no change in height. If you are moving 1 decade, there is no change in height. So the slope of this line is 0. Again, this is the line, the slope is decreasing, negative. So let's call it minus 20 dB per decade. Now this represents the slope. This represents the slope. This represents the height. So height at this point is 20 dB per decade, and this point the frequency is 1 radian per second. Now at this point, let's say the height is 10 dB. Let's say at this point the height is 10 dB, and let's call it omega 1. Let's call it omega 1. At this point the height is, let's say, 0 dB. At this point the height is 0 dB. And let's call it, look at this, let's call this point as 10 to the power 3, and let's call this as omega 2. Okay. Now one graph is given to you. Let's say some graph is given to you. In this graph, these heights are provided to you, and this frequency is given to you, this frequency is given to you. We need to find omega 1 and omega 2. Find omega 1 and omega 2. Find omega 1 and omega 2. So this graph is given on the log scale, and this height is in decibel, dB. Now we need to find omega 1 and omega 2. To find omega 1 and omega 2, it's very simple. You can use the concept of slope. You don't need to remember any formula for that. Okay. You need to apply the concept of slope. Now what is the concept of slope? We know that this line has slope of minus 20 dB per decade. Now what is the meaning of slope? Slope can be represented as change in height divided by change in omega, because this axis is omega. So change in height divided by change in omega, and height should be in decibel, and this change in omega should be in decade. So dB per decade, you have to calculate like this. This should be in decibel, this should be in decade, because it is, slope is given in decibel per decade, dB per decade. So this change in height should be selected as in terms of dB, and change in omega has to be selected in decade. So now look at this line. For this line, the slope is given, and the slope is given as minus 20 dB per decade. Okay, and we know the concept of slope. Slope is change in height divided by change in omega. So there are 2 points on this line. Now at this point, let's call it final height, because you are moving in this side. So this point will be the final point, this point will be the initial point. So you can take it like this. So now what is the final height at this point? And the height should be in dB. Height should be in dB. Now at this point you can say that the final height is 10 dB. Final height minus initial height. At this point the initial height is 20 dB. So final height minus initial height. And this change in height is in dB. Divide by change in omega. It means from this point to this point. This is the final omega, this is the initial omega. So change in omega is this. But you have to look at this distance in decade. Now how to check this distance in decade? It's very simple. Log base 10, you have to look at this distance in decade. So I told you how to calculate the decade, the distance in decade. Log base 10, the final omega divided by initial omega. Because you have to calculate the decade distance. So if you want to calculate this distance in decade, this is the final, this is the larger omega divided by the smaller omega. Okay. So this is the distance in decade. Okay. So we have calculated change in height divided by change in omega. And this change in height is in decibel and change in omega is in decade. Okay. Now this dB decade is cancelled. Okay. And now you can see that on this side it is minus 20, and this will be equal to, in the numerator you will have minus 10 divided by log base 10. Log base 10, and this is omega 1 upon 1. Okay. Now this will go on, okay, and here you have 2. Now you can take this on this side and 2 on this side, okay. So from here you can write log base 10 omega 1 divided by 1 is equal to 1 by 2, okay. You can write it like this. This 2 will go in the denominator. Now from here you can see that you can calculate omega 1 value. So omega 1 is equal to, this 10 will go, this 10 will remain as base. You can take anti-log, na? So this 10 will remain as base. So omega 1 is root 10. So you have calculated this omega 1 as root 10. I hope it is clear. So using the concept of slope, only, you can calculate this value omega 1. Similarly, you can calculate this value of omega 2. How to calculate this value of omega 2? Again, the slope is known to us. And the slope is in dB per decade. And we know that, so on this line, you can take 2 points. Let's say this is 1 point, this is the another point. Now we know that the slope has to be equal to change in height divided by change in omega. Now what is change in height? The final height is 0 dB. You can see that. The final height is 0 dB and the initial height is 10 dB. So final height minus initial height, okay? Final height minus initial height, you can see that. Final height is 0 dB minus initial height is 10 dB divided by change in this distance, and this distance has to be in decade. Now how to calculate this distance in decade? It's very simple. Log base 10 omega 2 by 10 raised to power 3. Omega 2 divided by 10 raised to power 3, okay? This is in decade. So this unit will cancel, dB decade will cancel. Now you can see that here on this side it is minus 10, here it is minus 20. So you can cancel this, so you'll get 2 is equal to 1 upon 2 is equal to 1 divided by log base 10 omega 2 upon 10 raised to power 3. So from here you can calculate omega 2, okay? So it's easy peasy. Tell me guys, I hope you can do it, okay? Now it is solvable. So it means if you have understood the concept of decade, how to calculate the distance in decade, if you have understood this, and if you have understood the meaning of slope, you have understood, then you can easily solve this type of questions. Let's take one more question. Let's say I get the graph like this. Let's say this is the graph and this is the height and this is omega on log scale. Okay, and let's say this is 20 dB per decade. The slope is 20 dB per decade. This point is omega 1, let's say 0.1 radian per second. And at this point, let's say the frequency is 2 radian per second. Okay. Now I call this frequency as 50 radian per second. And this height represented as K1 and this height represented as 100 dB, 100 decibel dB. Okay, and the slope is 20 dB per decade. The slope is 20 dB per decade. Okay, the slope of this line is 20 dB per decade. Now the slope of this line, let's call it omega 1. The slope is minus 40 dB per decade. Okay, let's call it minus 40 dB per decade. Okay, and let's call this as omega 2. We need to find omega 1, omega 2 and K1. We need to find these three things. How to do that? It's very simple. Using the concept of slope and distance, you can calculate this. Now let's try to solve this question. Let me change the color. Okay, now you can see that. Let's look at the first line. This is 0 dB obviously. At this point the distance is K1 dB because this x is in decibel. So this distance is K1 dB, this distance is 0 dB. So change in height, final height minus initial height. This is the change in height. Divided by change in length. This length you have to take. And this length has to be in decade. So log base 10, 2 upon 0.1. Okay, this is in decade. So we have calculated the slope of this line. final height minus initial height divided by divided by the change in distance. Okay, and this slope is already known to us, 20 dB per decade. Okay, this is already known to us. Now this dB decade will cancel, and you can calculate the value of K1. So K1 will be equal to, tell me the value of K1. K1 will be equal to 20 log 10, and this will be 20. I hope it is clear. So you can calculate this value, and you got the value of K1. You can calculate the value of K1. I hope it is clear. You can easily calculate K1. Now, if you look at this point, at this point 50 radian per second is given, and this height is known to us now. This height is known to us, and this height is also known to us. We need to calculate omega 1. So you can easily calculate omega 1. And this height is also known to us, this height is also known to us. So you can apply the concept of slope. Similarly, on this line, at this point height is 0 dB, and at this point height is 100 dB, and this omega 1 is known to us now, because from the previous slope you have calculated this omega 1. Only unknown is omega 2, so you can calculate omega 1 and omega 2 directly from the slope. So this is your homework. You have to calculate omega 1 and omega 2, and you have to comment in the comment section. Okay guys, so I think it's time to stop the class. I told you how to tackle these type of graph, how to calculate these values, omega 1, omega 2, and these distances. Okay, so this is important because this concept is used in Bode plot. Okay, this concept of distances and this magnitude, it will be used in Bode plot. The only thing is you must know the concept of slope and the distance. You must know the concept of distance also, because distance can be, because the slope can be in dB per octave. If the slope is given like this, dB per octave, then you have to take this distance in octave. If the slope is given in dB per decade, then you have to take these distances in decade. So you must know how to calculate the distance in decade or octave. Then only you can solve it. Okay, so the other concepts are simple. So I hope you understood this point, how to calculate these points. Okay, so this will be useful in Bode plot. I hope you have understood all these points. So this type of concept will be delivered in upcoming episodes also. So that's all for today's session, guys. Don't forget to subscribe our channel, and please like this session if you have understood these concepts, and press the bell icon so that you get the notification whenever my sessions are live. There is one more announcement. We have our mobile app on Google Play Store. So you can install this mobile app, and there also there will be some free lectures. You can take the advantage of those free lectures also. Okay, those free lectures are again, they will be useful for you because they are free of cost, the first thing. And the second thing is there will be so many conceptual lectures, so many numerical lectures, so you can watch those sessions on mobile app also. I'm also going to take some lectures on core subjects on the mobile app, so you can join this mobile app. So that's all for today's session, guys. I hope you enjoyed. See you in the next session. Next session will be on tomorrow 7 PM. So take care and bye.